Hi students, welcome you all. We are going to discuss second year 12th class chemistry, only important questions for the board exams. So we discuss only important questions. If you follow them, definitely you will score good marks. I am sure about that, and 100% pass. So few questions only we will discuss in every chapter. The first chapter, you know that in the second year chemistry is solid state, which carries 4 marks. They may give one 4-mark question or they may give two 2 marks questions, right? That 4-mark question also, it will come as a combination of two 2 marks question, right? Very few questions are there in this chapter. We'll try to discuss them. First, we'll go for 2 marks questions. In that, first question is, they will ask you that how can you distinguish crystal lattice and unit cell? This is the question. Very simple question, right? Just we have to write the definitions of them. How can you distinguish crystal lattice and unit cell? Very simple, right? So what is crystal lattice? What is unit cell? Simply I will give one normal example that some people are constructing a wall. So that a shape of the wall in three-dimensional space is a cube, right? What we are using to build a wall? Bricks, correct? So based on the bricks, they can construct a wall. That brick is unit cell, right? Because based on that brick only, the shape of wall, the structure of wall will come. And the total wall is called crystal lattice. So how can we say that a regular arrangement of, here bricks are what? Lattice points or points, you can say, right? A regular three-dimensional arrangement of lattice points in space is called crystal lattice. Correct? Points are bricks here. So unit cell is what? The brick. The brick means what here? The smallest unit of that wall, right? So the smallest unit of crystal lattice, which gives entire structure of that crystal lattice, is called unit cell. Very simple, right? So I will write, you can copy that, a regular arrangement. Which arrangement? Three-dimensional arrangement. That is the point. A regular 3D means three-dimensional arrangement. A regular three-dimensional arrangement of points. Points are here nothing but lattice points. Lattice points are nothing but what? Atoms or ions, right? A regular three-dimensional arrangement of points in space. In space is called crystal lattice. Is called crystal lattice. That's it. Very simple. So this is the crystal lattice. Now what about unit cell? Unit cell is what? I told you now, a smallest unit, correct? So unit cell will start that the smallest unit of crystal lattice. You can imagine that wall and bricks, then you can easily understand that wall and bricks. Wall is crystal lattice and brick is unit cell. So the smallest unit of crystal lattice, what is it giving? So which gives entire structure, means total structure, the entire structure of it, that is crystal lattice, of it is known as unit cell. Very simple. Unit cell. So the question will come that how can you distinguish Crystal lattice and unit cell. That is the question. So crystal lattice is what? Regular three-dimensional arrangement of points in space is called crystal lattice. The smallest unit of crystal lattice, which gives entire structure of it is what crystal lattice here, is known as unit cell. So this is one of the important question for 2 marks. Okay. 2 more questions are there. We learn them as differences, same like this. These two are combination will come for 2 marks. Now you know that everybody know that we were studying that intermediate second year. What is the next 2 marks important question, right? What is that? The next 2 mark important question is defects, right? Which defects? That also you know that. That is Schottky defect, and one more is what? Schottky defect, and one more, that is Frenkel defect. Here both of them are point defects only. Point means again here they may be atoms or ions. Schottky defect and Frenkel defect. Sometimes the question will come that write the differences between Schottky defect and Frenkel defect. I will write like a table. When they ask you for 2 marks, Schottky defect, define Schottky defect means you write that left side whatever we have discussed, and Frenkel defect right side whatever we have discussed, right? Schottky defect means the point defect in which the atom or ion missing from its normal position is called Schottky defect. Schottky containing S, right? So Schottky missing, that is also containing 2 S letters. Remember like that. All of them are S, Schottky defect, right? So here you can say that the point defect, correct? Both of them are point defects. The point defect in which missing of atom or ion from where? From its normal position. Or side, you can say normal position. The point defect in which missing of atom or ion from its normal position in a crystal lattice. Is called Schottky defect. Very simple, right? Schottky defect. Example, any one example you can write. For this example is sodium chloride, NaCl. So the point defect in which missing of atom or ion from its normal position in a crystal lattice is called Schottky defect. Here, I will try to make you understand from the diagram. For example, this is the crystal lattice. So this crystal lattice is containing points. We know that, right? Lattice points. What are those? They may be cations or anions. So cation means positive, anion means negative. Plus, minus. Same way here. Minus, plus, minus, plus, minus. Plus, minus, plus, minus, plus. Now here, minus, plus, minus, plus, minus. This is the crystal lattice. What we wrote here, the point defect in which missing of atom or ion. So here ions we have taken, correct? That ions are what? Missing, they are missing. For example, here one ion is missing, that is cation I am taking. Right? Here cation is not there. Cation is not there. This is called which defect now? It has some defect. What is that? It does not contain one cation. That is why defect. It has defect. Which defect? That is Schottky defect. In the same way, here to maintain the electrical neutrality, plus is not there means one minus also should not be there. That is called electrical neutrality. So from this anywhere you can say here minus is there, here is there, here is there, here is there, here is there. Any minus you have to remove. Correct? So I am removing this. So whenever we have removed one positive, we have to remove one negative also. That happens in the Schottky defect to maintain the electrical neutrality. So when positive is not there means negative will increase. Negative is not there means positive will increase. If both of them not there means it will become neutral. Correct? So this is called Schottky defect. This is the example. Now Frenkel defect. Still some points are there. We will discuss later. First we will discuss what is Frenkel defect now. So Frenkel defect, same. Whatever we are writing here, the same thing you will write. The point defect, as it is you will write. The point defect. The point defect. Whatever you have written, try to tell that the point defect in which. The point defect in which. What is that? Missing of. Here, one more word you have to add that. Shifting. Shifting of atom or ion. Here only one S is there. One S is there in the word means Frenkel. Two S are there means yes, yes. That is called Schottky. Just to not confuse. Sometimes they will keep that Frenkel defect subheading. They will write definition of Schottky. They may keep Schottky defect subheading. They may write the definition of Frenkel. That is why. So here this one is one S means Frenkel, two double S means Schottky. Because this also having one S. That is the point. The point defect in which shifting of atom or ion from same as it is written from its normal site or position, normal position. That is called Schottky defect only, right? But here what will happen? They will miss and they don't present in this crystal lattice in the Schottky defect. But in the Frenkel defect, whatever the missing cation or whatever the missing anion, that should be in the crystal lattice only. Here, these spaces are there, right? This space is called between this and here. Whatever the space is there in the crystal lattice, that is called interstitial position. So they will shift from the normal site to the interstitial position. For example, when you are in the classroom, that is perfect. When you are in the corridor, means what? You are shifting to corridor, right? So that is called defect. Which defect? Frenkel defect. So the point defect in which shifting of atom or ion from its normal position to interstitial position. I told you already what is the interstitial position. Interstitial position is nothing but gap between that atoms or ions. Interstitial position is called Frenkel defect. Frenkel defect. So there is the definition of Frenkel defect, and example is here. Write any silver halide. That is silver chloride. Here sodium chloride. Here silver chloride. The same we will try to draw a diagram for this. Here, this is the crystal lattice. So this is the crystal lattice. We have taken as is that plus minus, cation or anion, whatever, right? You may take the atoms also, A, B, like that. Nothing will happen. Anything you can take. So here, plus, minus, 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 plus, minus. So I told you that here missing completely that positive cation is not there and negative anion also not there. In this word, they won't miss, they shift. Means what? They moved from one position to another position. Whatever the position, that position they will vacate and they will reach another one, as I said you before the example. So here, this plus is not there, here not there. Okay, the plus is not there. Where is it now? The gap is called what? Interstitial position. Anywhere you can write, here or here or here, anywhere you can write. That positive is now, whatever you remove, that you have to write this. Means what? The normal position of this positive is this, but where it is present now? In the interstitial position. This type of defect is called Frenkel defect, right? And example and diagram is there. So if you want to write extra information, actually this is sufficient. You can leave here, right? Definition is there, example is there, diagram is there, right? Very simple. So what is that extra points? Extra points are here. It occurs in highly ionic compounds. Highly ionic compounds. So you can say this here. What is that point here? Come with that. It occurs in highly opposite. Slightly. You can observe the example here. Highly ionic compound example is NaCl. Slightly ionic compounds is AgCl. Slightly ionic compounds. Okay. So because of that, the coordination number is also high. So that you can write down. And one more here point. From this, if you observe the diagram, here one cation and one anion, both of them are missing. Means what? The weight of that crystal lattice decreased. When weight decreases, density also decreases. Correct? So coordination number is high, density is less. Correct? Density is decreased. So you can write that point. Coordination number is high and density what will happen? Decreased, because one cation is missing and one anion also missing. That is why density is decreased. Now easily you can write this opposite to that. Coordination number, CNO is coordination. Coordination number is low. And what about the next? Density increased. That is wrong. Density will not increase because a new cation or new anion is not coming. What happened there? The same cation or anion that is there in the crystal lattice only, but position is changing. Means what? Coordination number is low. No change in density. There is no change. No change in density. No change in density. Right? And the last point you can write that Na plus Cl minus. Na plus Cl minus. Both of them are having Na plus and Cl minus. Both of them are having almost similar size. Means what? Cation in this defect occurs in where that cations and anions are having nearly equal sizes or similar sizes. There what? The difference in the size is large in the Frenkel defect. That is the next point. So you can say that here the difference in size of cation and anion is very less. Very less means what? They are nearly equal size. They have nearly equal size. And here you can say that opposite to that, the difference in size of cation or anion, cation and anion is large. The difference is large here. Right? These are the points. If you want to write all the 4 points, you can write. If you don't want means this point is compulsory. Example and diagram, these two are very, very important. Otherwise, you may write any one of the point here also, you will get the marks. Right? So they may ask you only one means define Schottky defect means you can write this definition, example, diagram. Here also definition, example, diagram. Simple, Frenkel defect. When they ask 4 marks means you try to write more. That's it. Okay. So this is the one more important question in this. And the last important question. Everybody know that. What is that? Right. That is Bragg's equation. Very, very, very important. And compulsory question in the board exams. It may be any state. Very, very, very important. We'll try to discuss that in the simple way, not in the bookish language. In simple language, we'll try to understand it. Bragg's equation. Okay. So first of all, we'll discuss what is the Bragg's equation. The equation has proposed by the scientist named Bragg's. That is Bragg's equation. So what is it giving? The relation you should write. Okay. So most important question for 4 marks. Very, 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 very important. Compulsory question. Right. So derivation of Bragg's equation. Bragg's equation. I told you that what is Bragg's equation just now. What is the Bragg's equation? The equation has proposed by scientist Bragg's, right? So you can say that the equation has proposed. The equation has proposed by W.H. The full name of him is W.H. William Henry Bragg. The equation has proposed by W.H. Bragg, which gives relation. You know that, right? Bragg's equation is what? N lambda is equal to 2d sine theta. 2 is number. N is diffraction order. Lambda is wavelength. Theta is diffraction angle. Right? D is what? That is distance between two planes. That is called interplanar distance. So this total relation is coming from the solid, that Bragg's equation, right? So the equation has proposed by W.H. Bragg, which explain the relation, between what are those you should write? Interplanar distance, which is represented with small d. I will tell what is that in the diagram. Gamma. Wavelength represented with what? Everybody know that? Lambda. And diffraction angle or diffraction angle. What is that represented? Theta of what? Of X-rays. Is known as Bragg's equation. You can define like this simply. Bragg's equation. So what is that Bragg's equation? We have to derive. That is the main question. Not what is Bragg's equation. Right? The equation has proposed by W.H. Bragg, which explain the relation between interplanar distance, that is g, small d, wavelength, that is lambda, and diffraction angle, that is theta, of X-rays, is known as Bragg's equation. So before to derive this, we have to discuss one diagram, very, very important. For example, we have taken one crystal lattice. So this is the crystal lattice. We discussed that what is the crystal lattice? Crystal lattice is containing points which are called as lattice points. Correct. So those lattice points I am writing here. This is one lattice point. And this is one lattice point. This is one lattice point. We may take any planes here. This is called what? First plane. This one second plane. This one third plane. Third plane. All those planes are present in the crystal lattice only, right? So one X-ray is coming like this, right? It is coming like this. That is why I wrote that arrow mark. This one arrow mark. Okay. One X-ray is coming. This X-ray is called what? First ray. First ray. One more will come like this. One more will come like this. That is called what? We know that second ray. Okay, that is falling like this. So that is the first ray, and this one is the second ray. This is called second ray. Try to understand. So whenever we are assuming that the first ray is diffracted. Diffracted means what? They will take another way. Okay, the first ray is diffracted at point A. This is the point A. Yes or no? That is diffracting here. Point A. Correct. We are assuming that let first ray is diffracted at point A in the first plane. Okay. Next we can write that. Let us assume that second ray is diffracted at point B. Is diffracted at point B. In which plane? Second plane. So that is the second plane. Let's write whatever we discussed there. Let assume first X-ray, that is ray, first X-ray is diffracted at which point? Point we have taken that as A, point A, where in the first plane. In the first plane. First ray, first plane. Second one, let assume. What is that now? Second X-ray. Whatever I wrote in the diagram, that is what I am writing. Is diffracted. Second ray is diffracted at where? Point B. Point B in the second plane. Second plane. You may get the doubt, only few points are there. No, they contain so many points, lattice points, right? Here also from lattice points it has come. Here also lattice point. All of them are lattice points only, right? Here also lattice point. All of them lattice points. You may take any planes. But to explain this Bragg's equation, we have only two planes. To explain this, we required only two planes. Sufficient. Those are sufficient. So first ray is diffracted at point A in the first plane. Second X-ray is diffracted at point B in the second plane. Okay. If you observe that, which one is longer here? Either first ray or second ray. So obviously you know that there is second ray. Correct? So second ray is longer. Why? Because it travels more distance when compared with the first ray. That is the next point of us. That you can say that the second ray, the second X-ray travels more distance than first ray. Correct? Now the question is, the distance travel more, that extra distance is how much? Right? That extra distance travels is how much when compared with the first ray. Here, one thing also remember that the interplanar distance we have taken as D, means the distance between these two planes or these two planes here or here, wherever, we have taken that as d, small d. That is called interplanar distance. We wrote here, interplanar distance. Correct? Now come to this point. Here, this ray, when we are extending this ray, it will come and touch like this. Dotted line I wrote. Right? Hope you are able to see this. These are the dotted line. Here, this one is what? It will, when we extend like this, it will come like this, dotted line. So this A, this B, this one is what? C, because first ray. Second ray, here this one is what? D. Right? A, B, C, D. Now, what is this? The distance between point A and point B is equal to what? Interplanar distance only. What is that? How much? This is D again. Correct? That interplanar distance between 2 points, that is equal to the distance between point A and point B. D, right? And one more important point here. This angle is theta. This is called incident angle. And this one is diffracted angle, right? That is also theta. So here incident angle, the angle of incident beam is equal to angle of diffracted beam. That is one more point you should write, right? So here angle of incident beam is equal to angle of diffraction. Angle of diffraction. That is how much? That is theta. Okay. Now here extra distance is how much? If you observe that until here to here, both of them are same. Here, right? Both of them are same. Here also until here and until here, both of them are same. Extra is what? This distance and this distance. That is extra distance. What is that? BD plus BC. BD plus BC. That is the extra distance. Okay. So we can write that extra distance traveled by extra distance traveled by second ray is BC plus CD. Correct? Is equal to second ray equal to BC plus CD. This distance plus this distance, that is the extra distance traveled by second ray, BC plus CD. So which is integral multiples of wavelength. Integral multiples of wavelength. Okay. So this is a new point. I will explain this. The distance is equal to what? Extra distance is equal to integral multiple. That extra distance is nothing but what? Path difference. Path difference or extra distance traveled by second ray is equal to what? Is equal to integral multiple of wavelength. Okay. So we can say that here BC plus CD is equal to what? Integral means n, multiple of wavelength is what? Lambda. BC plus CD is equal to n lambda. Take this as equation 1. BC plus CD is equal to n lambda. You can take that as equation 1. So here BC plus CD, where are they? Here. If you observe, in this diagram we have two triangles, right angle triangles, those also. Correct? All of them are perpendicular to each other. So in the diagram we are not able to see, but all of them are perpendicular to each other. So triangle ABD. Yes, triangle ABD. So from this triangle ABD, for example, the triangle ABD I am writing here, right angle triangle ABD, right? This is a right angle triangle, correct? So triangle, from triangle ABD, sin theta is equal to, we know this, sin theta is equal to what? Hypotenuse by opposite, correct? So this AD is what? This one, AD is hypotenuse, right? Yeah, A is here, A, B, D. Okay. So ABD, sin theta is equal to hypotenuse by opposite. So that is called, hypotenuse is what? BD. Opposite to what? AB. This is hypotenuse, this is opposite. So hypotenuse BD by, so sin theta is equal to BD by AB. AB is what? Hypotenuse. Hypotenuse is AB is what? D. Therefore, BD is equal to what? D sin theta. Take this as equation 2. Right? Very simple. Now go for the next right angle triangle, that is from triangle ABC. Same way here. ABC. ABC. This is what? Hypotenuse. This one is what? Opposite. So from this, sin theta is equal to, hypotenuse is what? BC. Opposite to what? AB. That is equal to BC by D. Therefore, BC is equal to, again, D sin theta. Take this as equation 3. Okay. Now you observe that first equation, second equation, and third equation. So from equation 1, equation 2, and equation 3. Equation 1 is what? So from 1, 2, 3, BC plus BD. Correct? Here also BD. BC plus BD. So BC is D sin theta, BD is also D sin theta. So D sin theta plus D sin theta is 2D sin theta. 2D sin theta is equal to n lambda. So this is called Bragg's equation. N lambda is equal to 2D sin theta. This is called Bragg's equation. Bragg's equation. Okay. So this is about 4 marks. Very, very important question. Hope you got this. You can copy and write as it is. We'll get definitely 4 marks for this. Right. Thank you very much. We'll see in the next class with next chapter.